All right, I have started the recording. So anyone who does not wish to be recorded, please turn off your camera and your audio. Otherwise, I'm happy to be able to see my audience because that helps me know if I have totally lost everyone. The goal of the talk today is to give an explanation of what blockchains are and how cryptocurrencies work. This came out of the fact that I was teaching a Python course with a Stanford program called Coding in Place. And when I started talking to people, I realized a number of the people in this class didn't really understand what cryptocurrencies were or what the blockchain was or why this new class of asset was interesting. And I realized that this is really not that complicated. So my goal of this talk, and this is my first draft presenting of it, so I will try to refine it with whatever feedback you give me, is to give an explanation of cryptocurrencies for someone who has seen computer programming to a slight extent before, but doesn't have any particular experience in cryptography or security or cryptocurrencies beforehand. The goal is to very much start from the beginning and explain these technologies. So to give you a sense of who I am, I'm currently working at Twitter as an information security engineer there. This talk is unrelated to my work there, and any opinions expressed are my own and do not necessarily reflect those of my employer. I started my background doing PhD research at Georgia Tech, spent a brief period of time doing security at a nuclear power plant and radar research at the Georgia Tech Research Institute. From there, I went to Google and worked on their information security team, tried my hand at a couple of startups, and that brings me to Twitter. So I don't have any particular expertise in the cryptocurrency space, other than the fact that I am familiar with cryptography and the data structures that underlie them. So nothing in this talk should be construed to be like financial advice. So quick background. Why do we call these things cryptocurrencies? The answer is that at the very core of what these data structures are is cryptographic primitives. And there's two main cryptographic primitives that you need to understand to be able to understand cryptocurrencies. The first is a one-way function, also known as a hash function, also known as a cryptographic digest. And the second is a digital signature. Everyone here has signed a document in the past. The idea behind signing a document is we know that you agreed to this contract because you signed your signature at the bottom. Same idea with a digital signature. What is something you can do mathematically to prove that you saw this document and you agreed to this document at that time? So let's go through the four functions that are the only four functions you need to understand to be able to understand blockchains and cryptocurrencies. The first one is the hash digest function. The goal of this function is twofold. The first is that it will take a long message or a short message, and no matter how long the message is that you start with, the output will always be the same length. So if I wanted to cryptographically sign something that was a one-page document, I can do this hash and say, okay, here is this one code that represents this document. We call these hash functions after the idea of like mashed potatoes. If I have a potato and I make hash from that potato, and I give you this hash and say, here is a forkful of the hash that comes from this potato, which part of the potato did this come from? And the answer is, you have no idea. The potato has been totally destroyed. It's been all mixed up. Essentially, every forkful of mashed potatoes has a little bit of every part of the potato in it. This is the same idea with a hash function, that every bit in the output of your message digest depends on the entire input of the function. So if I change even one input in my message, I'm going to get a totally different number as the hash of that message. So I can use this as a summary. Just like if I had a story, I can have, Goldilocks and the Three Bears. I could go through and give you the entire story, Or I could hash it down to this one thing, and it acts as a digest of the entire story, because in some sense, the entire concepts that appear in the story now appear in this one message digest. But what we need is called a cryptographic hash function. So what makes a hash function considered cryptographically secure is these properties. The first is that it is hard to generate two messages that are going to have the same digest. So if I give you a message that says, give Aaron $1 million, it should be hard for you to make a new message that says, give Mahir $1 million, and get that message to have the same hash as my message. So it's hard for someone to swap out a message. You know that you have gotten the same thing. So you have the integrity of the message. If I have the message digest and someone gives me a message, I can tell, is this the message digest of this message? The second is that it is hard to directly generate one of these collisions. So if I give you a message digest and say, here is a particular number, give me any message in the world such that it hashes to this number, it is going to be difficult for you to find any random message that is going to be able to have that same hash. And the last property that is convenient is that the output is always the same size. So if my message is just 2 characters, hi, I'm going to get a message that is that same message length, typically 256 bits. Or if I give you something that is the complete works of William Shakespeare and I hash all of that, I'm going to get a message digest that is 256 bits in length. No matter how long that input is, I will always get an output of the same length, even if that input is nothing. One of the interesting things about message digest is you can actually have the message digest of the 0 bytes long string. So even nothing has a message digest, which can come in handy when you're trying to build protocols that have to start somewhere. The next thing we need to talk about is key pairs. So in essentially any cryptocurrency, you're going to have to generate some kind of wallet. And this is going to be defined by a key pair. And there's 2 parts to any key pair, hence the name key pair. The first is the public key. The public key is the thing that you can share with the world. So I can go to the world and say, this is my public key. I can give it to anyone in the world. And the second half is the private key or secret key, which I keep for myself. And as long as my secret key remains secret, I can take actions that everyone in the world can identify based on that public key, but only I can take those actions. So it relies on the ability of the person who owns the wallet to keep some kind of secret key secret while telling their public key to the world. So an example of where this would be useful is, say, in our world, we often use social security numbers to prove who you are. If I give you my social security number, that can be a secret. But if I've told one company my social security number and then they go to another company and say, hey, I need to prove that I'm Aaron, they could tell my social security number again. With a symmetric key, you can't really use that for identification. But if we had a public key system for social security, I could give my public key to every site on the internet, and there would be no risk of my identity being stolen as long as I kept the secret key secret. Only I could prove that I was the person who had that identity. There's 2 ways that we can go about generating this public key pair. The first is true random. I am just going to get random numbers from the air, use that to generate my key pair. And anyone who's able to find those numbers again is able to generate the key pair again. So usually you would save this as part of your secret that you keep around. Or you could throw away the randomness and just keep the secret key and public key pair. The other popular way to do this is to have a passphrase. If I generate my public and secret keys by using some particular password, as long as I still know that password, I can generate the same key pair again in the future and will always be able to access it. So for systems where you want to be able to keep your wallet in your brain, you're usually going to choose not some totally random string of characters that's very hard for you to memorize. You would choose a passphrase like you do for any website probably stronger than you do for any website. Some people don't need great passwords, but that's separate from this talk. You would choose a good password, memorize that password, and you could derive your keys from this password at any point in the future. You would get the secret key. You could share the public key publicly, and now you can keep information in some kind of wallet without ever needing to have a physical object that you keep. You can actually control a wallet simply with the contents of your mind and without needing to have a token or a hard drive or any particular proof. And the thing that's cryptographically strong about this is that it is hard for anyone to get that secret knowing the public key. I can give the public key to the world, and I have no fear that someone who knows the public key is going to figure out my secret key just by looking at the public key. All right, the third function, sign. So I have this public key and I have this secret key. What is this actually good for? The thing that we use the signatures for is to sign particular messages. So there is a kind of number that we call a signature that can be generated if you know the secret key. So I can take any message in the world that I want to prove that I have seen or prove that I approve of, and I can use my message digest function to make it a fixed length. And then I can use my secret key to sign that message and produce a new message that is the length of the key and the length of the message. And now this signature proves that I have validated that message and that no one else has. So if I have a message that says, Alice is going to give Bob $10, now Alice can sign that message, and we know that it is Alice who has decided to give Bob the money, and no one else could have forged that message. And of course, the thing that makes this cryptographically secure is that it is hard to generate those signatures if you don't know the secret key. So your best bet if you are trying to fake a signature is to just keep guessing secret keys until you get it right, and then use that secret key to sign the message. So it is incredibly inefficient and processing intensive to try and fake a signature. Then the last function is really the function that justifies the existence. We didn't generate key pairs because we like having key pairs, and we didn't sign things because we like having signatures. We went to all the trouble of generating key pairs and generating signatures because it enables us to do the verify. And signature verify is really the thing that is at the heart of any cryptocurrency and at any blockchain, is to say, I'm going to have a function where I can pass in the public key of the person who's making the claim. I can pass in the signature that they used to make that claim, and I can hash the message to say, does this in fact match? And any document that I have where I can hash the message, pass it into this function, take the signature that came with the document, pass it into this function, take the public key of the person who claims to have signed it, pass it into this function, and it will give me back one of two results. Either it will say true, this is a valid signature, I guarantee you Alice has actually authorized the transfer of 5 coin to Bob, or it's going to come back as false and say, either your public key is wrong, or your signature is wrong, or someone changed a bit in the message, but you cannot say that Alice has in fact agreed to the contents of this document. So this is actually much stronger than a wet signature. If you are entering some employment contract and you're signing your offer letter, if your employer changes one of the characters and says, oh, I actually offered you a different amount, your signature's at the bottom. They could totally take your signature off one document and stick it onto another. You can't do that with these digital signatures. If you move a signature from one document to another document, it's now going to fail because the hash of that document is going to have changed. The signature is going to be invalid, and validate is going to say false. This person actually never agreed to that contract. So congratulations, you now know all of the cryptography that is necessary to understand how blockchains work and how cryptocurrencies work. You have reached the state of the art of the cryptography that is the cryptocurrency. So now let's move on to the second part, because a cryptocurrency and a blockchain is two things. It is cryptography and it is a data structure. So what is this data structure that we call a blockchain? In order to have a blockchain, we need two parts. The first thing is we have a list of transactions that is the thing that we are trying to validate. So here I give an example where we are going to make up our own new cryptocurrency and our own new blockchain in the 35 minutes that this lecture is going to go on for. So we're going to start with JSON. JSON is the lingua franca of the web. Most web services that pass messages to each other are going to use JSON. So we can use this just as a simple way to get a wire protocol for our new blockchain technology that we are building. So let's look at the transaction. It's just a list of the individual transactions that are made by the users. So I am going to collect for some period of time all of the transactions. So Alice says that she wants to send Bob a milli coin, or Trudy says that she wants to send Eve 16 coin. And everyone is going to create their transactions and sign their transactions and then hand them to the miners. So the miners are going to simply take this document and say, okay, for the first transaction, are the signatures valid? For the second transaction, are the signatures valid? For the third transaction, are the signatures valid? And I'm going to throw out any transaction that is in this transaction log that was not a valid transaction. Now, there's a number of ways that a transaction could fail. A transaction might fail because the signature was invalid. Validate equals false, throw out that transaction. A transaction could fail because, say, Alice doesn't actually have the amount of coin that Alice is claiming to have. If you try to spend more coin than you have, that transaction is invalid and that transaction is going to fail. So we're going to throw it out and not let that onto our chain. And a transaction could fail because it doesn't know who the parties are. Maybe I've never heard of Bob. Maybe I've never heard of Alice. Maybe the transaction simply doesn't make sense or isn't well formed. We can throw all of those things away. What is the connection of the miners and the transaction? So the miners are the computers that are doing the work of validating all of the transactions. So the goal of people using this system is they want to know that every transaction is valid. The goal of the miners is to get the coin that they are awarded for successfully completing the transaction and doing work for the system. But they can only win their prize if they validate the transactions and if their validations agree with everyone else's validations. So they are incentivized to make sure that they are validating all the corrections and that they're not lying in their validations, because otherwise they won't receive the reward coin. Meanwhile, people are incentivized not to try and fake their transactions because the miners will realize that your transaction is invalid and throw it out. So everyone has these financial incentives to not cheat. So here we talk about also an amount, which is some number of coin that should be transferred. So here's the first trick that you see with most Bitcoins is that the actual numbers that they push around tend to be much larger than you think they are. So for example, a Bitcoin is a billion Satoshi, which is this sort of indivisible unit, but they always deal in some integer number of undividable pieces of coin because you really don't want to use fractions. Computers tend to cause problems with fractions. You never want someone to be like, I'm going to send you $0.33, because then you're going to get this like 0.33333 rounding truncation. You want to make sure we never truncate money and have small amounts of money in the extras wandering away from the world. So we solve this problem by having an atomic unit of coin and saying all transactions are going to be in the atomic unit of coin. So here we are saying, yeah, I'm sending 1,000,000 atomic coin units, but that's only 1,000th of one coin for our system, assuming that we've decided this typical, you should have billionths as the smallest amount of coin that you can transfer from one person to another. You'll also notice there is an ID on here. The idea behind the ID is to ensure that every transaction is unique. So if I were to send a transaction from my phone to this network, and I don't know if it went through, and I go, oh no, I had a network hiccup. I'm going to send my transaction again to make sure that it actually got through. Now the network is going to see two different transactions that have all the same data and have the same ID and go, oh, these aren't two different transactions. These are the same transaction. I'm going to throw this away. So this enables you to have an unreliable network and still a guaranteed once semantic. When I sign this thing that says Alice sends 1 milli Bitcoin to Bob, that Alice has sent 1 milli Bitcoin to Bob. No one can simply replay that transaction over and over again to send coin after coin after coin after coin. Once this thing has been signed and used to move some coin, it can never be used again. All right, so you'll notice the signature there was a kind of random looking string of characters. So I'm going to introduce a new concept here, which is base 32 encoding. The signatures is essentially just some 256-bit long number. But because we've decided that we're using Json as the protocol for representing our transactions, we can't actually put an arbitrary 256-bit number directly into JSON. There is no raw bytes feature of JSON. So there are four main ways that people will go about sticking arbitrary bytes into a JSON object. The first is hexadecimal. I'm going to use the base 16, 0 through F. You likely have seen some kind of serial number on something that's just a sequence of numbers and A through F. But this requires me to use 2 characters for every byte. So my 256-bit number is now 64 characters of this base 16 encoding. And that's very long. Now, I could go all the way up to base 85 and say, I'm going to use all the letters and all the numbers and exclamation point and a bunch of weird symbols to represent my arbitrary string. And that's going to be much shorter. My 256-bit number here is now going to be only 20 characters. So that's much shorter and easier to type in the sense that it's not 64 characters, it's only 20. But at the same time, some symbols look like other things. Is this a 0 or a letter O? Is this an I or is it the pipe symbol? It can be kind of tricky to type things in base 85. So we are going to take this intermediate ground and say, I'm going to use base 32. I'm going to use only 2 through 7 and lowercase numbers. It's not very ambiguous, and someone could actually type these in. It is not common that someone's going to have to type in a signature, but this does mean that someone is going to be able to type these things in without error. All right, so I had names there. You'll notice that in many of the Bitcoin systems, the addresses of wallets that you send things to are these long strings of random characters. In the system that we are designing, we want to be able to simply transfer to people using the names of those people. So we are going to add a new kind of transaction that is to name a wallet. And I'm simply going to say, okay, here's my transaction. This is the name I want. This is the public key that I want to tie to that name. And then I'm going to sign it to prove that I control the public key that I'm tying to that name. So now anyone who wants to can show up, generate a public key pair, and register a name. And just like we were able to check, hey, does Alice actually have 5 milli coin to send to Bob? Is this transaction valid? We can say, hey, is this name already taken? And if the name's already taken, we can throw out any transaction that is trying to take a name that has already been taken. Similarly, we can have capacities if we want to transfer ownerships of wallets to say, here was the old public key, here's the new public key, I'm going to sign it with the old public key. Now I can give named wallets away to someone else. This ability to give away a named object will become useful in the end when we loop back around to NFTs and how you would implement a non-fungible token in a system like this. So, okay, let's talk about blocks. When we talk about blockchain technology and public ledgers, we don't just talk about lists of transactions. We talk about a chain of blocks. So we need to talk briefly about what a block actually means. So here's an example block. I have some miner that has a wallet and says, hey, if I win this block, I want the prize coin to go into whichever wallet I have named. So this is a miner who is mining for Bob. And I have my transactions hash. So I talked about the fact that you could hash any document and you're going to get a nice short number that you can put into it. So we're going to take the list of transactions that were valid from everyone who tried to make a transaction in, say, the last 5 minutes and hash those down to one number and add that number to this block. So anyone who has this block can say, oh, here's the transaction hash. If somebody gives me a list of transactions, I can now validate that those list of transactions match the hash that's in this block. So no one can change the history. All of the transactions that happened in that list of transactions is now digested into this one digest number that essentially pins down everything that happened in that transaction. In a similar way to the fact that we can pin down the transactions, we can pin down the previous block. So this last hash that is in here refers to whatever the previous block was that got mined in the chain. So if we're making a new block, say every 5 minutes, I am going to know, hey, 5 minutes ago, this is the block that won. My new block is going to have the hash of the old block so that now no one can change the previous block. And lastly, we are going to add an ID that enables this particular thing to, again, be a unique transaction, a unique block. In most systems, you want to decide, yes, lots of people are making blocks that are candidates for being the next block. But there's only one block that is actually going to win and become the next block. So we use a pretty simple algorithm here, which is minimum. I am going to hash this block because, again, we've only got like 2 tools here, digital signatures and hashes. I hash this block and I'm going to get another message digest out from this block. And I'm going to say, whoever gets the lowest one, we are going to take the minimum of everyone who tried to hash this block, and they're the winner. Their block becomes the next block that is accepted into the blockchain, and they can give that candidate block to all of the other miners who will accept it and use the hash of that block as the last value in the next block. So now we have exactly one winner, and we have a bunch of people who are competing to win. Now, if I went and told another miner, hey, I won, here's my block with lots of zeros at the front, and I just make up some number that's a very low number, they're going to look at that and say, great, prove to me that your block actually has this hash. So I send them my block, and they're going to hash the block. And if I've just made up a number, it's going to be wrong because the cryptographic property of our hash was it's hard to find a block that is going to match a particular hash number. So your best bet to get a very low numbered block is to just keep picking random IDs and hashing it and seeing how low a number you got. And pick another random one and hash it and see how low a number you got. And the more processing power you have, the better your odds are of getting the lowest number you have. So this is the race of miners. The reason when someone is talking about how good a miner is, they say, well, how many gigahashes do you have? It's, okay, I have 1 gigahash. I can do this 1 billion times a second. I can pick some ID number, hash my block, check that hash to see if it's low. And if it's not the lowest one I found in the 5 minutes, I'm going to go back to the beginning and go again. Right now, for example, the Bitcoin hash rate, the entire community is doing about 70 terahashes a second. They are doing 70 trillion hashes every second, and whoever gets the lowest one by the end of the window is the person who ends up minting the next block and winning the coin as prize. So if we think about these blocks, well, I can give you just the message digest of the most recent block, and you can use that to prove the most recent block. But of course, it has a last pointer in it that will give you the hash of the block before it. And I can hash that and check that it matches the hash to prove the block before it. And this keeps going recursively back. The 2 blocks ago validates 3 blocks ago, and 3 blocks ago validates 4 blocks ago, and 4 blocks ago validates 5 blocks ago. And this goes all the way back to the second block and then the first block. So in any cryptocurrency, there is what we call the origin block, which is the very first block, and it has no last pointer. Or because hashes can actually give you the hash of nothing, we can actually have the first origin block point to the hash of the empty thing and say no bytes, like the previous thing on this is nothing. In that way, we can start the origin, and the very first origin block can have the transactions and say, hey, I'm creating a wallet. My wallet is named Satoshi. I'm mining for Satoshi. I'm going to hit the first time and I'm going to get 50 Bitcoin. And now, as of block number 2, there's one wallet that exists and it's got the 50 coin in it. And now we have a world in which there is some amount of coin in the world, and we can start trading amongst each other, creating new wallets, moving forward from that origin point. So the reason we call it a blockchain is just that simple. You've got a block that validates the previous block, that validates the previous block, that validates the previous block, back to the beginning of time with the origin block. This chain of blocks is a blockchain. But each block in the blockchain also points to a list of transactions. So I have all of the transactions that have happened since the dawn of time. And I know that all possible transactions are validated by that. So if I hand you just this one head digest, I have now pinned down the most recent block, the most recent set of transactions, every previous block, and every previous transaction. All of the transactions that have ever happened from the beginning of time are now pinned down and can't be changed. This is what we call a public ledger, because all of the transactions can be publicly viewable, and anyone who gets the head block now knows everything in history. And if I now come back and say, hey, I want to change history, I want to pretend that a year ago something happened that didn't actually happen a year ago, I can't change the history because everyone in the world has already, or at least everyone in the mining pool has already learned about that history, and all of the blocks are based on that. I would have to essentially try to replay all history from the time that that happened until now and create a better set of hashes and a lower hash for every single block between the time I wanted to change something and now. And because I can't actually produce better lower hashes, because I don't have more computation in this 5-minute window than everyone on the entire community had between when I want to change something and now. So it is a immutable history merely because there is a proof of work, and I cannot actually do enough computational work to change the past. So let's talk about how many coins exist in the world. If you follow Bitcoin, they talk about the fact that there's like 21 million-ish Bitcoins, and there will never be any more than that number of Bitcoins. So we have to have a max number. In this case, we've decided we're doing JSON coin here, and we're going to represent everything in JSON. So what is the largest integer that we can represent in JSON? And it turns out the largest number we can represent in JSON is about 9 million billion. And we've decided that we are going to use 1 billion indivisible pieces to be our coin. So we set a nano coin to be 1 atomic unit, which means our micro coins are 1,000, our milli coins are 1,000,000, our coins are 1 billion, etc. This means that in this system, there can never be more than approximately 9 million coins, because we would simply run out of space. That is the largest integer that we can put into a JSON object. And we would start getting rounding errors if we went past that. So let's decide how many coin we want to give as a prize. So in most blockchains, and this is somewhat different for some of the newer blockchains where people will choose different economics for how to assign out the coins. But the traditional answer is you want to give out about half of the coins and then slow the rate at which you give out the coins, and then give out another half of the coins and then slow the rate at which you give out the coins. So in our theory here, we are going to say we're going to do 5-minute blocks. Every 5 minutes, we're going to mint a new block. And every 100,000th block, we are going to reduce the amount of coin we give away. So this means we are going to reduce the prize about once a year, because that's how many there's, 525,600 minutes in a year. So by giving every 5 minutes, there's about 100,000 of these blocks in a year. At first, we want to really encourage people to mine because nobody uses our coin. Our coin's not that valuable. So we have to give a lot of incentive for anyone to bother mining because the coins just aren't worth that much. So we give them 50 whole coin every time they hit. Once a year has gone by and we start getting popular, if we didn't get popular, like our coin is dead, so it doesn't matter. If we did get popular, the coin is going to be worth more now, so we can cut the amount of prize down to, say, 20 coin. And then a year later, down to 10 coin. So now every year we give away half of the outstanding coin into the world, and the value of the coin continues to inflate in price over time as more and more people are using this cryptocurrency, but more coin is coming into the world so that we can continue to incentivize people to mine. Eventually, though, this is going to start getting low. After it's been, say, 30 years, there's only going to be 5 coin that are being, there's only going to be 5 nanocoin that are given out for the prizes. So eventually you're going to have to switch over from funding the miners by giving out newly created coin to funding the miners with some kind of taxes, where we take a percentage of every transaction and give that to the miners. So how much coin is the actual max in our system? Well, 5 + 2 + 1 is 8, where in this cycle of there's going to be 10, and then 5, and then 2, and then 1 in each of the sections of our thing. So in every digit, there's going to be essentially 8 of that magnitude prize that are given away. And we give away at each level 100,000 times. So we now get to this number of the amount of atomic coin that we've given out is this 8.888888 million billion atomic units of coin, or about 8.8 million coin. And this fits. We have picked the right size for how much coin to give out and how much to decrease each year so that it will always fit within this JSON number. So even if all of the people in the world sent all of the coin in the world to one wallet, that wallet could actually hold all of the coin and we have a safe amount. So that guarantees us safety within the JSON number. All right, names and subnames. So we want to add names to the system so that we can just refer to like Alice and Bob rather than some crazy number. But once we add names to the system, we can start adding rules to that. So I can say, okay, names are not allowed to contain a slash. If you have a slash, we're going to call that a subname. So now Bob can make a number of wallets like Bob's Savings and Bob's Phone and say, okay, I'm going to keep most of my coin in my savings account and I'm going to put a small amount of coin on my phone so that in case I lose my phone, like, yeah, they can empty that wallet, but they can't like take all of my money, and I'll gradually move stuff into my wallet that I use out in the world. But more than that, you could do it for organizations. So Georgia Tech could have a wallet and say, well, within Georgia Tech, we're going to have a sub wallet that's the math department. And maybe the math department wants to say, well, we've got a bunch of number theorists, so we're going to have the numbers lab. And one of the guys in the numbers lab is Gawa, so he's going to have his wallet. And now we have a way that you can actually store organizational relationships, where this person, Gawa, can say, hey, I'm totally a member of the numbers lab in the math department at Georgia Tech. You can tell because I have the secret key that goes with the public key that has this structure. Or someone like Bank of America could offer Bank of America / account number and say, we're going to make every account at Bank of America also a wallet. And we can decide what the rules are for these subnames. So maybe the rules for a subname is you can rekey yourself, or if the person who is one tier up from you decides to rename it, they can rename it. So if like Georgia Tech decides this math department has gone too far, we're abolishing them and starting a new math department with a new key, they could change the name of their subkey. And this is going to come in handy later when we want to say, prove identity as part of an organization or have something that you give away. So for example, if I wanted to do a NFT, a non-fungible token, I could just use name reassignment and say, hey, I am Nike, and I'm going to make a subname that is Nike / this model number. And this model number is going to have a subkey that is this serial number. And I'm going to issue a cryptographically signed name for every shoe that we made in this particular model. I could then assign those keys out to whoever the current owner of the shoe is and allow the other person to rebuy it. So this gives you the ability to use these public ledgers to track ownership of art or collectibles or anything that you would want to use a non-fungible token for. All of this sort of falls out of a relatively simple structure of names and subnames. So validating transactions. Every time that you have one of the miners to a transaction, you need to decide, is this transaction valid? So each type of transaction is going to have its own set of rules that says, here's how you validate the transaction. So the simplest one is send money. Alice wants to send Bob a certain amount of coin. Is it Alice's signature? Is the signature valid? Does Alice have the amount of coin to send? Is Bob a named wallet in the system? If everything comes out true, then it goes through. For something like registering a key, you just have to claim the name that you want to name. Or creating a subname, you're going to have to say, oh, I'm making this new subname. It goes to this new key. And I'm going to sign that transaction as the person who owns the name and thus has the right to issue subnames. But these transactions could be arbitrarily complicated. So on networks like Ethereum, they have what they call smart contracts, which is you have this transaction that you want to be validated, except in the transaction, you can put arbitrary code and say, I want you to run this piece of code. If this piece of code returns true, it is valid. If this piece of code returns false, it is invalid, and have all of the miners essentially take the transaction that you're trying to run, take that data, pass it into the validation, custom validation function, run that smart contract, and see if it's valid to make things happen. In the one that we're designing now, because we only have like an hour to design a cryptocurrency, we are going to skip that and say, you can't do your own validations. We are simply going to allow you to have renaming things, subnaming things, and moving coin around. So there you have it. I've taken you through our initial explanations of what a cryptographic hash function is, how digital signatures can be used to build identity into the system, how the validity of transactions can enable us to have the entire transaction log of history. And by reading that transaction log and calculating up how much coin each person has, we can decide whether future transactions are or are not valid. And through the use of names, we can have a non-fungible token, the ability to give strong identities that can be used on this chain or off on other chains. So I think that that covers a lot of the value that people get out of cryptocurrencies, and that this is relatively understandable. You don't need a degree in computer science to understand a message digest is just a short number that comes from the message. A signature is just a number that can be validated, that only one person could have ever generated that number. A blockchain is just a bunch of data structures that have hashes of the previous data structure. And a public ledger is just the list of all of the transactions that have happened since the beginning of time that have been tied down by one hash. With that, I would like to open it to questions. And we will take about 5 minutes for questions, and then I will stop the recording and ask if anyone has offline questions.
I have a question.
Go ahead.
Obviously, listening to what you said, what what makes blockchain so valuable then?
So generally the idea, so at least the way Satoshi described it in the first paper that proposed blockchain, was its value was simply that it made better money. If you want to do, say, a wire transfer between two American banks, it's going to take you like 3 days to move the money from one place to another place. And you're going to have to pay some kind of fees to the bank in order to move that money. The idea with blockchain is sort of the same idea as gold. Gold made good money because it was relatively portable. You could take it from one place to another. It's highly divisible. You can cut a gold bar into a bunch of slips and give someone just part of it. And it is a common medium of exchange. Once lots of people think it's valuable, it's a lot easier to carry around gold. So I can say, sell all of my sheep for gold and then buy wheat over the course of the year as I need food or supplies or whatever. So it is a good store of value. Most people don't actually need gold, but gold made a good currency because of its scarcity and divisibility and portability. The idea with a digital currency like this is it is incredibly portable. You could send this kind of money through a text message. You just say, hey, dude, what's your wallet ID? They give you the ID and you send them the money. So you can send it through any channel you have ability to communicate through, internet, SMS, anything. It's highly divisible. I've set my coin size to 1 billion atomic units of the coin. So maybe I can divide my dollars into cents that are hundredths of a dollar, but it's actually kind of tricky for me to give you 1/millionth of a dollar. Nonetheless, 1 billionth of a dollar. So the high divisibility, the high portability, and the scarcity that comes from the fact that I keep decreasing the amount of it in the world, and eventually, even after the first year, half of all of the coin in my chain that will ever exist for all humanity will already exist. So you're not going to have to worry that suddenly someone's going to like strike a gold mine and the amount of gold is going to hugely increase in the world and it's going to tank your economy. Like there is a predictable rate at which more of this cryptocurrency is going to come into the world. So it provides all of the same things that make gold valuable as a currency, except for gold, people just seem to happen to like. And cryptocurrency, people just seem to happen to like, and you just have to hope that you picked a cryptocurrency that gets popular. If it never gets popular, it won't be a good money. Does that make sense?
Yeah, it does. It does.
All right. Do I have any other questions?
When a project starts a blockchain or maybe some kind of cryptocurrency, and the founders are kind of minting the tokens for themselves, so the way that they control that then is just by virtue of not allowing others to go and mint at the beginning. I'm trying to figure out like how they kind of maintain control over the blockchain and the tokens, for example, at the beginning.
Right. So at the beginning, the miners are the entire network. So if I sat down and wrote the code to implement this thing in my presentation tonight, I can mint the origin block and just sit there and win every block for some amount of time. And I'm going to get 50 coin for every time I win that block. Now, this is a trade-off for someone who's making a new coin. So if I'm making a new coin and I wait an entire year before I tell anybody about it, and I win the first half of all the blocks and take half of all the coins that will ever exist, chances are my coin's never going to get popular because people are going to look at that and go, oh, Aaron's got half the coin that's ever going to exist. If he ever sells, it's going to tank the whole market. Like, this is a dangerous coin to be invested in. Aaron can totally ruin it. But if I say, oh, I'm going to start mining on this date, and I invite people to come in and say, I'm going to win the origin block, and I'm going to invite you in starting the 5 minutes after that, then I'm going to start building up a community and I will get trust for those early adopters. That said, the sooner you join any community, the more likely you are to win the early blocks, because traditionally it's very easy to win the early blocks and it's very hard to win the late blocks.
In most projects, just to follow that, most projects, they kind of control those early adopters or early.
Yes, a lot of projects will have a sort of limited beta. I'm only going to let in people I know at the beginning, and we as a community are going to win the early blocks, and then we're going to open it to the world so that anyone can start winning blocks. And if you too quickly open to the world, you're not going to make much money off of your coin. This is what happened with Dogecoin. The guy who created Dogecoin pretty much immediately sent it out to the world and won the first few blocks, but was basically done from there and barely made any money off Dogecoin. If you wait too long to invite the world in, no one's going to use your coin and it's going to be dead on the vine and you're not going to make any money. So there's sort of this balance of you want to be greedy enough that you make some money, but you want to be selfless enough that your coin doesn't just die. Although there's certainly people who think the moral thing to do is immediately go public and not try to monetize the fact that you got there first and you made the coin.
Thank you.
Aaron, I guess you might put it like, until enough people were interested in gold, it wasn't enough of a commodity for it to make sense to use, right? Like similarly.
That is true, but gold had a cheat for how it got started. So there was this guy called Attila the Hun, and he tried to make a very large army so he could take over the steppes. But it's really hard to feed a giant army. So he decided that he was going to have this rule, which was he was going to pay all of his soldiers in these gold coins. And he was going to tell all the people and territories he controlled, at the end of the year, I'm going to collect gold coins and you have to be able to give me gold coins or else I'm going to do violence to you. So by creating taxes in gold coins that people had to pay, suddenly there was a massive demand for gold coins in order to pay Attila's taxes, which meant that Attila could now use the gold coins to pay his army because people would sell them food because they needed the gold coins to pay their taxes. So he used taxes to create value for gold in sort of the same way that the US dollar is highly unlikely to lose all of its value because I need a certain amount of US dollars every year. I have to pay my US taxes in US dollars, so I have to get US dollars. So the core thing that is propping up the US currency is taxes in the United States have to be paid in US currency. And the thing that was propping up gold was that Attila the Hun's taxes had to be paid on a gold standard. And we see that as governments around the world have abandoned the gold standard, the value of gold has tended to become less important to economies and the value of the currencies we tax in becomes more important. Cryptocurrencies don't have this advantage because what are the taxes that prop up a cryptocurrency? Oh, it's the tax you have to pay in order to transact on the blockchain. Why do I want to transact on the blockchain? Only if that's a valuable currency. So it is not yet clear to me what is going to create or sustain value in a cryptocurrency. But that gets into more economics than the cryptography. All right, with that, I am going to stop the recording and then give people a chance to ask questions that are off the recording if they are curious. So I will stop the recording.